to have everyone here so late in the day. Did you enjoy the conference up to now? That's good, cool. We won't keep you too long, we'll try not to go over time, but we've got an exciting topic for today, and that's, we need to, so I can see the slides here, but, oh, they're just delayed, that's good, okay. We're gonna be talking about vector databases, and you might have heard about them in the past couple of months. That's also why we picked up the topic. There's been a lot of buzz. On the one hand, a lot of funding, so I think like 350 million just in the past months put into different startups. Also, you might have noticed that a lot of databases that you might have used are suddenly talking about vector as well. So we thought, okay, that's a good topic to bring to this conference today. And I guess maybe the first question to ask is, has anyone here used a vector database? I talked to you before. I talked to you. Okay, good, cool. That's pretty good. So you will learn today what vectors are, what we can use them for, and what the role of the database is. And for the start, I'm going to hand over to Bruno to talk a little bit about vectors.
Thanks. So let's start and let's try to keep this flow easy. What is actually a vector? It's a motorcycle and a bicycle, basically. It is basically a representation of a dimension placement of an object or multiple objects. This one is a very simple one. So basically, we have motorized and no motor objects. And you see there is a very simple vector that is mathematics definition about position in a space, right? So to keep it a little bit more complex, we have here multi-dimension representation of the vector. So what you see here is that similar data is grouped together. So we have basically no engine vehicle that is moved on land. We have engine vehicles moved on land. We have here vehicles that are moving on water and with no engine and engine. And you see there is a sailing boat which may have an engine. So in the representation of a vector, we will have basically those two, car and the motorcycle would have approximately the same values. The bicycle would be somewhere else. And then you see the sailing boat is basically have a different value. Should be here something else. Why? Because it also may have an engine. So it is near to this vector. That's the basic principle of vectors.
And I wanted to ask, does anyone have an idea of what a three-dimensional vector could be? Maybe one that you've used before? Does anyone have an idea for three-dimensional vector? Have you used the GPS system, maybe? So a coordinate is also a vector, obviously, right? So we can also, these are two-dimensional, and if we have a three-dimensional vector, it could be your placement on the X, Y, and Z axis. But I guess that has been around forever, right? Sailing boats, ships, bicycles. We never used vectors before, so there must be something new to it. And the exciting part here now is that if you look at all of the AI models that we have popping up around us that we're all probably using in our everyday lives with ChatGPT and so on, essentially what these models themselves, so the AI models, not the applications around it, what they produce is what we call embeddings, and embeddings are vectors, just that they don't have 1, 2, or 3 dimensions, but very often they have tons of dimensions. So you can look that up on the models. They might have hundreds, they might have thousands. And what you can see on this schematic here is these vectors and also the dimensions are not so tangible for us humans anymore. So before we had motorized, non-motorized, so basically motorization as a vector dimension, and we had the location in terms of sea, air, water. What we get from those deep learning models is all kind of abstract representations because they go through these different layers of the neural network and they come up with their own most efficient explanation of the world in terms of these vector dimensions. So you will get dimensions and numbers. But that's actually the reason that makes this interesting because we can now use this to understand language, for example. So on the right-hand side, and I'm hoping you can also read this from the back, we've got a couple of vector representations of man, woman, king, and queen. And so those are the words that we're vectorizing. And we picked out a couple of different dimensions. So there's, for example, the dimension living being, the dimension feline, which is like cat-like, human, gender, royalty, verb, is it a verb or not, plural. And then what a language model can do is it can map us these words to different representations of the data. And we will be able to see if you now try and, obviously this is now a two-dimensional reduction, so it's not mathematically correct, but the interesting thing is that in vector space, the vector for man and for woman will be quite similar together, because even though the gender is different, all of the rest, living being, human, and so on, is quite similar between those vectors. So they will be similar. Same thing for king and queen, right? They're both royalty, they're both human, and so on. It's again just a gender that is different. So this is actually now how we can employ AI models to create such vector representations that express some kind of meaning about the data that's put inside. Thanks. And essentially what that enables us to do is do something that we like to call vector search. So if you're now looking to build IT applications that use those AI models, we can build all kinds of different applications for all kinds of scenarios. So essentially, let's look at the right side first. The way this works is similarly to what I've just shown you for the word embeddings. You can do that with your text documents, you can do that with your images, audio files, videos. There are even some multimodal AI models out there. And for each of these, you could be creating a vector. And now if you're looking for something, like an image that you're looking for in a collection, you would do the same thing. So you pick your image, you again create a vector of it, and then you go in there, you do some magic to find the similar things in vector space, and you pull them out for your users. Now, what are the use cases that we can do? At the simplest, this could be something like location, so going back to the geographical vectors, like find me the nearest supermarket to my location, right? But it could also be finding similar products. So we had a nice workshop this morning about, hey, let's drag in an image of something that I like into a web shop, and can you find me the products that look similar to this one? It can be finding similar users for recommendation. So you already have a user, let's say you're an audio application, you have a nice user with a big playlist, new user comes in, selects a couple of songs. How about we calculate that similarity and see what to recommend to that person? More in a business context, very often it's about finding similar documents. So you might have a snippet of something or like a question. Can I find some document in my existing data store that I already have? Or also fraud cases, or actually anything basically that you can find an AI model for that will generate an embedding. So that's kind of the mindset, right? Getting more specifically into those use cases, one example I think that's going to be very interesting in the next months or next year is how this will be transforming product search, right? So if you look at a traditional shop, your web shop interface, currently, you're just putting in your keywords like whatever, I need to build an irrigation system, so I'll make up some keywords like PVC, that's the material it's made of, I need some plumbing, and it's for an irrigation system. But essentially, now that we're all using AI, what we want to get to is that we want to be able to actually ask our shop like an actual question, give it more context. For example, I'm trying to build an irrigation system for my actual backyard, which has a certain dimension, it has a certain location, and I would love for that shop interface to come up with the right products. And this is an excellent use case for getting into a similarity search. And I mean, if any one of you has ever tried to find something on like a construction site, website, that's terrible. So I'm really looking forward to this. One use case. Second one, image search. So you might have crashed your car, like this poor person, and you want to get a replacement piece for this. At the moment, the search is usually, oh, do you have the parts number? No one has the parts number. And maybe if there's an image database of cars that had repairs, because obviously it's similarity search, so you're not going to find the part that's missing, but you might find the part that's related. That could actually help you find the right part number for this product. I think one use case that you probably heard of today if you attended some of the other sessions is using vectors as a long-term memory for language models. Now this is a bit different from the pure similarity search approach that we saw before. The challenge with using language models on something like your business data is, on the one hand, that the language models are all trained on public data sets, so they have no idea of your sort of private data sitting inside your organization or company or your users' data that they have on your web application, for example. Now, while you can fine-tune a language model to other data points, very likely that data is going to be changing much faster than you want to be doing that fine-tuning cycle, right? So really the solution here is, again, to use vector search basically on two parts. So on the one hand, we're getting the question of the user. We're vectorizing the question to find a nice data point in vector space with the language model. And we're doing the same thing with our business data, like in the diagram I showed before. So no matter whether it's your documents or your images, whatever you have in your organization. And then we're creating a context, what we call a context window. So essentially, for this vector of the question, pull out the most relevant, by using vector search, the most relevant pieces of documents from your business data, and then just send this context window to, that can even be a cloud API, to something like an OpenAI model, which has been trained on the public data, and tell it, hey, based on this context window, can you answer me that question? And that is a very relevant use case for vector search that we are seeing in our day-to-day projects at the moment. Final use case that we're going to quickly talk about is fraud detection. I think we all know that fraud is a big issue, and there's been some machine learning-based anomaly detection where you basically scan some time series and you look at the graphs. Do we have outliers? But vector is another way to interpret this, right? So you can think of modeling whatever a user is doing in your system. So that could be a financial transaction system, for example, or it could also be a website where you do some shopping. And you can, based on these actions, on the clicks, on the user data, you can create something like a fingerprint of the activity of that user. That fingerprint can easily be represented as different dimensions of a vector. So each kind of action type, has it been done or not, the sequences. And then we can put all of that again into a vector space, and you can imagine it kind of like small, dense clouds of data points forming for normal stuff that's happening. And then at some point you might have some data point that's outside of the normal range, and those are actually the ones that we want to pick out because they might be fraudulent cases. And that's actually building a model of what's normal in your system and cases that are extraordinary. The same, by the way, that you can do with fraud also always works for problematic cases like, your system isn't working. So it's interesting to look at it from two perspectives. You might also find unhappy users and maybe make them happy on your next release. Good. Next. What's under the hood of these vector applications? Let's not do too much mathematics at this point. It's 6 p.m. already. But one important thing, I now talked a lot about putting things in vector space, many dimensions, and vector similarity. So what's actually going on? The one concept you need to understand is that we're always doing something called the nearest neighbor search. And this means, so you have one point, and from all of the other data, you're trying to find the other points that are closest to this one, no matter how many dimensions, right? And in the mathematical literature, the nearest neighbor search is a hard problem. So you need to scan a lot of data points. So there's some algorithms that make this easier. And two things to differentiate when you're later on maybe looking at some candidates for vector databases that you want to use. There's something called the k-nearest neighbor search, which limits the search to say, hey, I only need the 10 nearest neighbors, not 20, not 100, I need exactly 10. So that's one way to make the whole thing faster. And there's something called approximate nearest neighbor, which is give me about 10 of the nearest neighbors, and if maybe one of them is not really the nearest, but there would have been another one that's actually by definition nearer, I don't really care. It doesn't need to be exact. And this is much, much faster. So depending on your use case, you should be smart about selecting the right algorithm. And essentially what it does, there are different types of similarity metrics. So how do you even compare a vector that has 1,000 dimensions, right? There needs to be an algorithm for it, and you will find one of the most widely used ones is cosine similarity, and essentially this is a simple two-dimensional vector. These two vectors would be very similar. These are completely unrelated. The value is 0. And these are opposite to each other, so they are also the exact opposite of each other. So that's kind of what to look at when you're now trying to implement something later on. Be wise about choosing the right algorithm and the right level of exactness. Another interesting part of this, what you will see in the implementation, is called hierarchical navigable small words. So this is essentially the idea of your classical search algorithm also projected to vector space. So what does it do? Again, you might have a million of those vectors if you're indexing, I don't know, let's say all of the emails of your users. So you need to make this faster. And essentially, it divides your data into different layers, or it builds different layers on top of your data. And it kind of groups your data together into buckets. So at the bottom layer here, this would be your actual data. So let's say, one vector for every sentence in an email. And up here, it's already pretty much grouped. And up there, you can see there's only three more groups. And so when you have a query coming in, you're trying to find something similar, you first pick the most similar one on the top layer. That sends you to a certain entry point on the second layer. Then you pick the most similar one here, and it sends you to a data point down there. And that significantly reduces all of the search time necessary. So this is an algorithm that a lot of vector databases currently implement in slightly different ways. Pardon? What's that? Oh, you need. Oh, sure. Go ahead. Good. Perfect. No, I'm not going to photobomb. Good. So I'm not going to kill you with this slide, but just to give you an idea, there's some nice papers you can download. Probably put some in the notes and for whoever wants to have it at the booth. But basically, depending on your use case, you would want your vector database to implement very different index types, right? Because they have different characteristics. So if you're trying to do image search, there's something called product quantization, which splits the image down into different parts. So that would help you find something, let's say in your database, you have an image of a dog, but there's also a tree in the lake. And what you're searching for is the image of a lake. So you would want that original image to be kind of split so someone can find the lake in it. But there's also other index types in your database that are optimized for spatial queries. Like I want to have all of the delivery trucks that are currently within 100 kilometers of my town. And there's also others like the one that I just showed you, the HNSW, which is really good for text search, for example. So just to give you an idea that this is not like a one-size-fits-all thing. It makes some sense to just superficially look into what is it that I'm actually trying to do, and then pick the right thing. Good. So that was a lot of theory, but our talk is about databases, right? So now let's go to the database.
Yeah, so at the end, you want to have this data saved somewhere on a way that is a safe place, efficient, reliable because of fault tolerance, and maybe also scalable because you have lots of data. So, and there is a lots of, I would say, processes that needs to be take care of from the side of a database. So basically, the most important part is you have to think about what you want to do with this use case. So we have here as a comparison two different database models, in this case relational and vector database. And you know that a relational database model is tables with rows and columns. In vector database, you will store vectors in a native format. So, which means it would basically do much better and much faster similarity search. Like we heard already that vector databases are actually search databases. So this is the use case for them. So it can be a positive search, you look something that's similar, or negative search, you are basically looking for something that's not in a raster, so it's a fraud or something like this. And there is also the question of performance. So relational databases would be transactional databases focus on ACID. And vector database is basically optimized for high throughput. So it means basically that it would not be your source of truth database, right? And then to go a little bit deeper, we have also document databases where you can actually save unstructured data. Some of them are also used for vector storage. Basically, we have search engine today. In today's workshop, we had Elastic, which is a sort of document database, and based on it, we were actually doing the whole thing. So just thinking of time, what to choose. So basically, you have more or less multiple possibilities. So you can use a native or dedicated vector database. You can start with open source, but also you have some commercial or sort of commercial possibilities, or take one of the other databases that has a library to store vector systems in a sort of native way, like Postgres or Elastic, what we saw today. So the question would be, if you're using Postgres for your application today, for relational database, for tables, rows, and so on, maybe it is easy to implement something on top of Postgres. If you want to basically start a totally different approach and you would like to have lots of similarity search and you have lots of unstructured data, maybe you can think about using Elastic. By the way, Elastic is open source since 2 weeks, again. Yeah, so you can use it freely. And then there are some features that are also important for vector database. When you think about them, it's alignment between data structure and vector data storage and index. Why it's important? Imagine you have a search and you're looking for a document, you're looking for a black dog and a white cat. You will have probably multiple documents with the same search. So what you want to do is basically to narrow the search on the specific documents where this can occur. And you don't want to have this, the results, to show you the results from a single document because it's always there. A second idea is if you have, let's say, a web shop and you're selling, I don't know, clothes, then you can also filter out, if you're looking for, I don't know, t-shirt for men, you can also basically narrow your search on 20% because probably 80% would be something for women. So this is basically what is important. Then also, not all systems are supporting the same number of dimensions, which is important of the search quality. You have to think about algorithms that are natively supported, like Gregor showed you. It's not every single algorithm is good for maybe your use case. So this is this part, and just example.
Yeah, good, cool. So yeah, I mean, just quickly jumping back, right? So you see, there's all of these differences, and you have different databases with different feature support, but in the end, developer productivity is really important and usability is really important, right? So the screenshot that I just took, and you mentioned Elastic, it's a tool that we work with quite a bit. But just to give you an example that this can also be very easy, and I like very much the way it's been implemented here, because in the end, you can run your AI model inside the search cluster. So even though you've heard all of the talk about algorithms and databases and persistence layers, in the end, as a developer, what it can look like for you is essentially you have a JSON file and image, that's your source data. You're shooting that sort of directly into the search engine as you did before. It's JSON, you put it in, you get full text search. But you also put it through your embedding pipeline, which is running in the cluster. It's a second post call. And basically it's adding you one line in here, which is the embeddings, and you're done. And then you need to define a query, but that's basically just a second step. So don't be overwhelmed by the complexity. It does make sense to select based on your use case. As Bruno said, if you already have a database, probably a good first step is to simply try it, because probably you selected the database because it kind of fits your data model, right? So, people use Elastic because they have document-based data they want to search in. People use Postgres because they have data that fits the relational model. So why not start with that? And then afterwards, if it doesn't work well, look at those dimensions, those ideas we gave you, select the right algorithms, the right database type, and try it with that one. Next slide, please. Final slide, final word also on benchmarking. If you start Googling about vector databases, of course, vendors will be talking about their performance. That's what vendors do. Don't trust the benchmarks that the vendors themselves come up with. They are often very much tailor-made to the specific functionality they support, right? So if I'm a database vendor whose main asset is that I support 50,000 dimensions, I'm very likely going to be running benchmarks that really showcase those dimensions. So there are alternative benchmarks, like open source ones, and I just picked one by Eric Byrne. It's a widely acknowledged benchmark suite. So if you're interested in the performance of the vector database, so let's say you're trying to roll this out to a big web shop and you need to make sure this is going to be scalable for 50,000 concurrent users, and you're selecting technology based on that, do look for independent benchmarks. But then again, if you open this page, you will see that it's not so straightforward. So put in this screenshot, this is an example of the GLOVE dataset, which is a machine learning dataset with 100 dimensions. But if you try the same databases with 1,000 dimensions, the graph looks different. So it doesn't make sense to open the benchmark page before you know what you're doing. So first look at your scenario. Okay, this is my, my expected load. This is the AI model I'm going to use. It's going to have this and that many dimensions. And also like the type of data that I have. Which of these example data sets does it mostly correlate with, right? So a GLOVE data set has words, but there are also image data sets and so on. So it would be unwise to use the benchmark for a word-based data set if you're trying to use to do image similarity, right? So that's kind of the process you need to go through, and then you can make sense of the benchmarking data. Yeah, that was the final remark of the talk. I hope this quick tour through vector databases and why we think they're really important right now made sense to you. I'm happy to take any questions if you have them. Questions in the audience? No questions at the moment. Yeah, so we have a booth. You can't miss it. It's a circle. If you go around the circle, we're on the outside left. We have our AppCont logo. Feel free to stop by if you want to chat, discuss. Also curious to hear, for those who have experimented, what your success has been up to now. And thanks for staying with us for so long.